Your job is to find the volume of the solid. I'm going to write down the formulas for the three different shapes that we have here. I'm going to do problem 4. The rest of them are going to come out to whole numbers. So the cone is 1/3. The radius here is 5. Remember, we don't want to use the diameter in the formula. We want to use the radius. Then we've got a pi and a height of 7. 5 squared is 25. 25 times 7 is 175. And then the numerator is 1. So 1 times 175 is 175 on the top. And then we have 3 on the bottom. We're still leaving our answer in terms of pi, so that should be included, as well as our units. As I mentioned, the other 4 problems are going to come out to whole numbers, meaning if you have to divide by 3, the numerator will be divisible by 3. This is the only one that should be left as a fraction. An empty cylindrical container has a base with a radius of 2 feet. A liquid is poured into the container at a constant rate. The table and graph show the approximate volume of the liquid for selected heights when 3.14 is used for pi. Does the table represent a function? If so, explain why and write an equation that represents the function. If not, explain why not. This is a function because each input goes to its own output. There is one output for each input. And since it is, we need to write an equation that represents the function. Let's figure out what the slope is. It says that it has a constant rate, so it should be a constant slope the whole way. The way that we find that rate or that slope is going to be subtracting the y values, subtracting the x values, and then dividing. So 1570 minus 6.28 is 9.42. 1.25 minus 0.5 is 0.75. And then we're going to divide those two to find the slope. Which is a slope of 12.56. You may recall this formula that we used for finding the slope. Now, if the item has no height, it should have no volume as well, so the initial value should equal 0. So to turn that into an equation, y equals mx plus b. You don't necessarily need the plus 0. You can remove it because adding 0 is not going to change this value. The cylindrical tank shown contains water that is 1 foot deep. More water begins flowing into the tank at a constant rate of 10 cubic feet per minute. The water flows for 20 minutes. Write an equation that represents a function for the approximate volume of water V in cubic feet in the tank T minutes after the water starts flowing. Use 3.14 for pi. Well, we know what the rate is, but we do need to know the initial value to help us figure out what the b or the y-intercept of the equation would be. We know it starts with 1 foot deep, but we need to know how much volume that is. So we have a radius of 3 times pi times the height, which is 1 foot for the volume of water that's already in there. So 3 squared is 9, and then 9 times 3.14 is 28.26, and if you multiply that by 1, it's still just 28.26. So our volume is 10 cubic feet per minute, which is T, plus the initial value, which is 28.26. You could think of this as Y and X. The only difference here is that they're using V for the volume and T for the time. But it's still in a y equals mx plus b format, or a slope-intercept form. Then it says, if water flows into the tank for 20 minutes, will the water overflow the tank? And explain how you know. So we're going to replace that t with 20, because it's 20 minutes, and t represents minutes. 10 times 20 is 200. Plus 28.26 would be 228.26 cubic feet. Now let's figure out how much the entire tank can hold. It has a radius of 3 and a height of 8. 3 squared is 9. 9 times 3.14 times 8 is 226.08 feet cubed. So will the water overflow? Yes, since it's got 228.26 and that is greater than 226.08, the water will overflow. This is how much it can hold, and this is how much water will be in there after 20 minutes. 3. An hourglass can be modeled by 2 cones that meet, as shown. The hourglass measures time by the flow of sand from the upper cone to the lower cone. Each cone has a radius of 5 and a height of 8 centimeters. The sand flows from the upper cone to the lower cone at a rate of 15 cubic centimeters per minute. When all of the sand is in either the upper cone or the lower cone, it fills the cone completely. Functions represent the relationship between the volume of sand, V, in cubic centimeters, in each cone, and the amount of time T in minutes after the hourglass has been turned over. A asks us to find the approximate volume of sand in the hourglass by using 3.14 for pi and rounding our answer to the nearest tenth of a cubic centimeter. We had a cone, so that's 1/3 radius squared times pi times the height. In this case, our radius was 5, and our height of each cone was 8. So 5 squared is 25. Then we'll do 25 times 3.14 times 8, which is 628. So we multiplied 5 squared by 3.14 and 8. Now we need a third of that, so we can multiply by 1 and divide by 3, which is 209.3 repeating, but the 3 leaves it as a 0.3 when it's rounded. B says, what is the initial value of each function, and what does the initial value mean in this context? The terms lower cone and upper cone refer to the parts of the hourglass after it has been turned over. So when we first flip it over, the lower cone has no sand in it, so the initial value is 0. And it represents that there's no sand in the lower cone right when we turn it over. The lower cone is empty. But for the upper cone, all the sand starts there, and it's going to start to pour into the bottom as time goes on. But it starts with all of the sand, which is 209.3. C says, what is the rate of change of the function, and what does it mean in context? Well, let's go back and read the original part of the problem. It tells us that the rate is 15 cubic centimeters per minute. So for the lower cone, that rate is 15, and it means that 15 cubic centimeters of sand is flowing into the cone each minute. The bottom cone is getting more and more sand. But the upper cone is going to start to lose sand. So that rate is going to be negative 15, which is 15 centimeters cubed of sand is removed or lost or fallen each minute. D. For each cone, write an equation for the function that describes the volume of sand, V, in cubic centimeters in the cone, T minutes after the hourglass has been turned over. So this one had a rate of 15 and an initial value of 0, whereas the upper cone is losing sand each minute, but it started with all of the sand. Again, you don't need this plus 0. You could just write it as V equals 15T, but it's not wrong to include it if you'd like to. E. Hourglasses have historically been used as timers. About how many minutes does it take for all the sand to leave the upper cone and enter the lower cone? Round to the nearest minute. So we want the upper cone to have a volume of 0. or we want the lower cone to have a volume of 209.3. So let's use this function here. We want all of the volume to go to the lower cone instead of being in the upper cone. To solve this for t, we would divide both sides by 15. (209.3) divided by 15 is approximately 13.953 repeating, and it says round to the nearest minute, so it'll take about 14 minutes. So this would be a 14-minute hourglass timer. 4. An ice cream scoop makes scoops that are essentially spherical with a 3-inch diameter. This ice cream scoop is used to take scoops out of a full cylindrical ice cream carton that is 11.5 inches in diameter and 11 inches in height. A function represents the relationship between the approximate volume of ice cream, V, in cubic inches left in the carton, and the number of scoops N that have been removed. A, what is the initial value of this function, and what does that number mean in context? Use 3.14 for pi and round to the nearest hundredth. That is 2 decimal spots. Well, the initial value is going to be all of the ice cream in the carton, and it told us that the carton was a cylindrical carton, so we need the volume of a cylinder, which is radius squared times pi times height. It doesn't give us the radius, it gives us the diameter. So to get the radius, we need to divide the diameter into 2 parts, which is a radius of 5.75. So 5.75 squared times pi, which we're using 3.14 in this problem, times the height, which is 11. So 5.75 times 5.75 gives us 5.75 squared. Then multiply that answer by 3.14 and 11. We're rounding to the hundredth, so we're keeping 2 decimal spots. Since this one here is above a 5, we need to round up. So that is 1,141.98 inches cubed. That is the initial value, and we also need to state what it represents. That is the amount of ice cream in the carton. B, what is the rate of change of this function? We are changing by scooping out sphere-shaped pieces or sphere-shaped scoops. So we have the volume of each scoop is 4/3. The radius in this one would be half of 3, which is 1.5, cubed times pi, which we're using 3.14 for pi. So we have 1.5 to the third power, then multiply that by 3.14 and by 4, and divide by 3 because that's in the denominator. This is 14.13. Now the rate of change, we're actually scooping ice cream out or removing it. So the rate would be negative 14.13 because we are removing it from the carton. I guess I should say this is the B value. And it represents the amount of ice cream removed with each scoop. Now we need to write an equation for this function that describes the approximate volume of ice cream in cubic inches left in the carton after n scoops have been removed. So our rate and our initial value. Remember, this is just like y equals mx plus b, but instead of y, we're using v for volume, and instead of x, we're using n for the number of scoops. How many full scoops of ice cream can be removed from the carton? Assume that all ice cream in the carton can be scooped. So we need the volume of the carton. If it's all removed, the volume would be 0. We're going to subtract 1,141.98 from both sides. Then divide both sides by negative 14.13. And that gives us approximately 80 for n, but it says how many full scoops can be removed. We can't fully remove 81, so we can remove 80 full scoops. Since this doesn't quite reach 81, the most scoops we can remove is 80 full scoops. That is the end of Module 6, all of the volume questions combined.